we're going to expand and enrich the model by allowing an infinite number of types, an infinite number of messages, and an infinite number of actions. I've been using the idea between the doctor and the patient intentionally because I'm going to be making an analogy at the end using data on coronavirus. However, I don't really mean doctor-patient. I mean more like medical statistics. So whoever is producing medical statistics is going to be called a doctor. And the patient is going to be called anyone who is reading this information and trying to infer what is the state of the world. Stage 1, nature, chooses the type, chooses the state of the world, which we call X. And this time it's going to be uniformly distributed along the unit interval 0 and 1. X is not only the state of the world, it represents the so-called truth, quote unquote. Stage 2. First of all, the doctor in stage 2 observes what nature has chosen for him as his type and sends a message encoded as some information, which we call I, which is also going to be included within the interval 0-1. And he sends the message to the patient. Then there is stage 3. The patient observes the message or the information, as we've so called it, and chooses what to do. Say how long he will wait to undergo the surgery, where undergoing a surgery now is equal to 0 or in a year is equal to 1. So his action is going to be called Y. Again, an infinite number of actions contained within the unit interval. We know the sequence of play from this. However, what are the payoffs? So our payoffs now are going to be slightly different. The patient's payoffs, again, are going to be very similar to the payoff of the doctor, dependent only on the true state of the world and his choice, and is equal to minus x minus y to the power of 2, which is a quadratic equation. This utility function is called a loss function that minimizes the mismatch between his action and the true state of the world, where the maximization of the function is the minimum. So the doctor's payoff is very similar to that of patient. However, it has an extra element. It contains a parameter, which we've seen before, so minus x minus y minus b squared, where b is the bias, which before we called the tendency for malpractice. So essentially what the bias does is that it measures the conflict of interest between doctor and patient. So I'll show you this on as a graphical representation. Our x-axis, the choices that the patient can take to either undergo the surgery today or undergo the surgery in a year, bound by the unit interval. And the y-axis is simply the utility function. We are going to assume that the true state of the world is here, which is the exact moment in which the patient should indeed require the surgery, the true state of the world. But the bias of the doctor, let's assume, okay, I'm just giving you an example, sits here. He wants to get the surgery done as quickly as possible so that he can make money off of the surgery, say. All this means is that this is the ideal action for the doctor, and this is the ideal action for the patient. And since our utility function is quadratic, we have a bell curve, but it's also a loss function, which means that the maximum is going to be at 0. So in the case of the doctor, we have something like this. If we should maximize this function, The first order condition tells us that y, so the y, at maximum is equal to x minus b, which is equal to 0. Now imagine there are two alternative recommendations. Let's say that the doctor can recommend y1 or y2. It is possible to make a comparison between the two recommendations from the point of view of any player, since the utility functions are symmetric. And this is the type of assumption that we're going to be introducing into this new formulation of the game. So now that we've fully described the game, what is our solution? So again, we're going to be talking about finding babbling equilibria and trying to really determine how we can discover what are the conditions under which separating or partially separating equilibria exist. Because pooling equilibria are easier to analyze, we start with those. What are pooling equilibria? Pooling equilibria in cheap talk games are called babbling equilibria. For this specific description, it means that all types send the same message, which in other words, mathematically, means that types are statistically independent from the messages. All types are behaving in the same way, which means the patient receives no information at every information set. The patient holds the same belief and therefore acts based on his prior probabilities. Again, this is what we're saying. Priors are equal to posteriors. There is no meaningful communication, no transfer of information. We find one construction for this equilibrium and generalize it like we did before. Assume all doctors recommend surgery now, which in other words means that m equals 0. So the message is today, no matter what state of the world reveals to her. The doctor's message does not depend on the state of the world. In this case, patient's beliefs will be equal to his priors, and patients will maximize accordingly given x is between 0 and 1. So just reminding you that this is the state of the world. Maximize the utility function of the patient with respect to y. Correct? And this is what it looks like. And then take the first order condition. The first thing you have to do is just simply open up x minus y squared, which should give you minus x squared plus 2xy minus y squared. Okay, you take the first order condition, so maximize with respect to y, we get 2x minus 2y and 2x minus y. Oh, and I forgot a bracket up here. Which means that our expectation is now 2x minus y equal to 0 at maximum. What we want to do is we want to isolate y. We want to find our best response for the patient, right? Y star. And we remember the rule for expectations, or we learn the rule of expectations at this very moment. Because the expectation of the sum is the sum of the expectations. And because y is a choice variable, it is not random, which means that we can exclude it from this expression, just like we can exclude the other constant in this expression. Y star equal to the expectation of x. And since x is uniformly distributed between 0 and 1, y is equal to half. Therefore, y given any message, will always choose the position half. So after any recommendation, the patient's choice is going to be half. The action of the patient is always a half if the belief of the patient does not depend on the message. For any M. This is our babbling equilibrium. No matter what the doctor says, we always take the same action. It makes no difference whatsoever. His recommendation is completely ignored.